Yeah. So, yeah, welcome to the second leg of the Aerosol Science and Technology course. So, in previous lectures by Professor Chandra, we were introduced to the fundamentals of aerosols, starting with the concept of size distributions, the mechanics of aerosols, motion of particles with or without external forces, and a very central and important concept called the Brownian motion. Then the consequences of Brownian motion, transport associated with it. Then of course, very important application like light scattering. If you notice, most of the aspects that were examined were single particle effects. That is, we basically examined the motion of single particles or Brownian motion of single particles or light scattering by single particles. The overall aerosol effects are linearly added to obtain the ultimate endpoint effects. However, there is a very important collective effect in aerosols where it is not just the single particles, it is necessary to have all the particles with all their size distributions together to describe the behavior. And one such most important process is called coagulation. So, it is inherently a nonlinear mechanism because it is collective. Its interaction between the particles is very important. Now, why do we need to study that? It is fine to say there is a nonlinear mechanism, but why do we need it? In fact, coagulation as a subject started long before aerosols became a commonplace topic. However, the importance of that phenomena is uniquely experienced in aerosol science. For example, Professor Chandra in our introductory lectures did mention of aerosol size spectrum, right? We have modes like this, aerosol sizes. This is x-axis, which is diameter, and this is some number distribution. And we have something called an accumulation mode here. So, there is a coarse mode. We understand the coarse mode. It comes from top-down approach, larger particles breaking up, dust and etc. And this accumulation mode predominantly is dominated by the build-up process of particles which are generated as sub-nanoparticles, basically molecules and maybe clusters of molecules. But here several maybe 100 nanometers beyond that, we again get a peak and no particle is produced there, mind you. So, to explain any such occurrence of a not so obvious behavior or a pattern, here we have to invoke the way particles agglomerate or coagulate and grow to that size. To be precise and to quantify, you need to build a mathematical model. So, coagulation provides such, at least partly, if not fully, because there are many other mechanisms of course in play, but predominantly to explain such behavior. So, as we know that particles are formed by many ways, one by breakup, which is the coarse particles, and by build-up. And this build-up process is actually multi-step process. And all the so-called important aerosol that we talk about, which are important for climate or important for health effects, they all are generally built from the lower end, not all of them, significant part of it, like a combustion source, for example, is a very well-known example. Photochemical from the atmosphere, gas to particle conversion is another. So, all these mechanisms build up. So, if one has to look at the steps that is involved, first you have the step of formation of, say, formation of particles which it is in fact called formation of monomers, you can say. So, a monomer in an aerosol terminology is that primary unit which late has a tendency to grow. Thus, if you have carbon dioxide molecule, it is not a monomer because it does not accrete on its own, it does not grow on its own. On the other hand, if I have an H2SO4 molecule as a monomer, then it has a tendency to evolve further. So, a monomer is that primary unit formed through a series of chemical reactions, but which now constitutes a further growable unit. So, that is the first criteria. Now, these monomers, most of the vapors can condense on them. There is a free energy reduction. We will come to that point in the next topic that we are going to cover on nucleation and growth. So, I am going to take it after this coagulation lectures. So, that is an important mechanism that these so-called monomers, which would be just very tiny clusters, they condense vapors like this and then they could be growing. So, first there is a nucleation of the monomers, of course, and then there is a growth, and it is at this stage that large number of such monomers, order of 10 to the power 12 or more per meter cube, then they tend to collide with each other and grow in a collective manner, and that is what the coagulation phenomena is about. Yeah, any question? What do you mean by chemical? Let's explain. Right. So, that part of the chemical mechanism is essential for all agglomeration to grow or all for particle formation, right. But most of, I am going to come to that, the most of the chemical aspects, they occur at extremely small length scales of the orders of sub-nanometer or angstrom level length scales, whereas the rate controlling step always happens to be the transport mechanism down to that distance, and we are studying that transport mechanism. But you are right, ultimately it is very important to have those chemical forces. Otherwise, as I mentioned, carbon dioxides collide far more frequently than aerosol particles, but they do not grow at all. So, there the chemical forces are weak, binding forces are weak as compared to the thermal agitation. So, that is always hidden. We do not need it explicitly to model it because it is a sub-nanometer process. We have to carry the particle down from several micron distances to that distance, and that is what we are discussing in coagulation theory about. So, given this background of what why we need coagulation, we can more specifically therefore bring it together, all these ideas to define the process. Although in literature, if you see, there are so many words, right. You have, for example, you have a word called accretion, you have agglomeration or aggregation, we have words like flocculation for bubbles. There is clustering also is used quite often. Like the rice condensed becomes it accretes, becomes hard. In some way it is also an aggregation mechanism, but it does not involve the kind of kinetics that we are going to study. So, coagulation is that kind of an accretion mechanism or growth mechanism where there is some kind of a mechanics that goes into the transport itself. Otherwise, many times one would interchange them, of course, coagulation with the aggregation also. Perhaps the contexts only differ. Primary principles might remain the same. Mechanisms could be the same. So, here we are essentially focusing on fine particle coagulation, whereas aggregation could be of much larger systems also. Granular aggregation is there. There are many models, but we are talking of fine particles in the range up to 1 nanometer to maybe 10 nanometers about. Of course, there is a further coagulation in the whole raindrop is ultimately a product of coagulation which takes place, not part of it at least, and that is a large particle coagulation. Early theories of coagulation in fact did start with having to explain the formation of millimeter sized drops from 30 microns rain clouds, particles. So, they included lot of theory of how gravitationally differential velocities make them hit together and then how the particles grow. Probably we will not dwell into that topic. Here it is very introductory, just to give you an idea of what coagulation is all about. So, fundamentally what we are going to discuss is there are particles in a system. It is very necessary to have many particles and they then collide with each other. So, that is collision rate. Collision by itself does not cause coagulation. So, we have to make some very important question now, as we mentioned about what happens at the time of collision. So, we invoke sticking as a phenomenon that brings in irreversible growth. So, that irreversibility brought in by the concept of sticking. So, you have collision, then you have sticking. So, these two together, they sort of cause what we call as coagulation. Then they grow to larger sizes. Now, there are possibilities many a time. Again, we are not going to deal with that. The possibility is that the aggregates also can break up. It can happen even for raindrops. In fact, raindrops do break up at times. But these are very specialized topics. Some of them are under great investigation even today, because the modeling of breakup is very important in many contexts, but we are not going to deal with breakups much. We are going to deal with this irreversible growth only. So, this system of activities or system of behavior of particles is going to lead to finally the formation of the size spectrum. So, in that sense, very interestingly, coagulation is the mother of generation of polydispersity. So, even if you started with all monodispersed particles, eventually you will end up with the polydispersity, because the rates at which particles will collide will have fluctuations, and that will lead to a size distribution. So, occurrence of size distribution partly is because of the process of coagulation. We should keep in mind, of course, there are other mechanisms of growth like flocculation in colloidal systems, coagulation, but often called as flocculation of bubbles, for example. Then we are going to deal with another mechanism of condensation, is called surface growth often. So, that also we are going to deal with, where monomers only come and stick to your particle and make it grow. Sometimes this condensation is called attachment. When you are attaching monomers are very dilute, not like water vapor, but some trace elements, for example, in the atmosphere, when they stick to a preformed particle, that is called attachment. The science mathematics remains the same, so more or less, but a special terminology is used. Or when ions come and stick to particles, it is called attachment. So, that is also another concept used. And coagulation theory has a fairly interesting history. So, as I mentioned, much before the aerosol science got formalized as a subject, the concept of aggregation was introduced by more or less practically by Marian von Smoluchowski, a celebrated name in coagulation theory. There were others before him who were wondering why, for example, ink flocculates, right. So, people were trying to explain, and the concept of Brownian motion did not exist at that time. So, what is it that makes them come together and then form larger particles? So, but then soon Einstein's theory of Brownian movement came in 1905. Perrin did experiments in 1908. Brownian motion was confirmed, and then it was Marian von Smoluchowski said, by just connecting Brownian motion of particles with the concept of sticking, I can generate structures. And to demonstrate that, he developed what we call today as the coagulation equation. So, M. V. Smoluchowski, he can be rightfully called the father of coagulation theory. More or less it remained as a very important fundamental subject in colloids, but in colloids it was not really that ubiquitous or necessary or important phenomenon, primarily because of the very strong double layer repulsion forces. They are all charged particles, they hardly agglomerate. So then of course we developed subsequently the DLVO theories, the Darjigin, Landau, I'm forgetting the names, Walmer at the end. They all had to bring in models to explain, to bring down this repulsion charge by salting and all that, and Debye's theory of coagulation came, of course. But in aerosols, primarily the developments on coagulation were because of people like Nikolai Fuchs, who is the founder of aerosol science, more or less, although of course N. Fuchs, although Whitlock, Gray and Patterson had already formulated the subject of aerosols and smoke, but he actually brought in new models for coagulation, basically from a physical chemistry standpoint, but very much applied to coagulation theory, and he take it to a level at which really there has been no greater development than that later. Today most of the coagulation models that we use are based on Fuchs models. So he made a great contribution. Then of course this Sheldon Friedlander, he adopted the coagulation model to explain the formation of psi spectrum in the atmosphere, and also to the theory of aerosol reactors were introduced by him. So applications became more diverse, and he brought in the concept of so-called self-preserving size distribution. He is the first one to have formulated the concept of similarity theory in coagulation, to identify the similarity variable, and that is basically what self-preserving distribution is about, and we will deal with it in the course of our lecture very briefly though. So all that we see is coagulation is very ubiquitous. It occurs in most dispersed systems, clotting of blood in biological systems, in galaxies, formation of galaxies. Chandrasekhar's paper 1943 does discuss these matters, application of Brownian motion in astrophysics. And one important noteworthy fact with the coagulation is that if I have a system of particles having some mass concentration, say phi mass per unit volume, then coagulation process conserves this mass concentration. So that is a signature. If tomorrow you are seeing some change in aerosol and you have to go backward, do reverse explanation, the data you will subject to a test whether the decay that you have observed in your instrument has conserved mass or not. If it has conserved the mass, then it could be coagulation leading to that. Could be, not necessarily the unique. Compared to that, you see a growth mechanism in which only condensation is acting. So I have 4 particles and monomers are condensing. Then each of these particles will grow to a larger particle, let us say. Here you would notice that this would conserve the number. You will not see a change in number, but you will see a change in mass concentration. So if there is a change in mass concentration by conserving the number concentration, one would suspect that the mechanism was some kind of a surface growth or condensation. So these are very useful, valuable, broad pictures to analyze if you have an experimental data which is far more complex. Like for example, if your number concentration came down because of loss to surfaces in an enclosure, this also can bring down number concentrations. then this would change both the mass concentration as well as the number concentration. So the overall change could be a complex effect of all this. So that is why the next step that the aerosol science took after the coagulation theory was what is called as the general dynamics equation. It's a very foundational equation to describe the mechanics of aerosols, and that includes all these processes together. So in which coagulation becomes one term. So it's important to understand that particular rate processes. Now you will ask a question: if coagulation takes place ubiquitously, and if it is about sticking of the particles, then how come water becomes a sphere, remains as a sphere, liquids remain spheres, but many other particles like metal, vapors and all, they grow into very ramified structures. And in many reaction engineering, it is important to get spherical particles. So the process of coalescence now gets added on along with sticking. So you have now one more criteria. They are brought together by mechanics, they stick and then they coalesce. Coalesce means they basically move around each other. They don't get out, no breakup, but there is a movement around that, and that phenomena, that is if there is no such movement, then you are likely to get aggregates in which both volume and surface area are conserved. Whatever surface area monomers had, you will have the same surface area in the aggregate if you calculate. If you use a BET method or something, and you will get this roughly the same surface area. That is irreversible sticking you see in metal particles, and liquids as shown here, they sort of spread around each other and form a sphere. So there is a theory developed by Wolfgang Koch and Friedlander in 1990 to understand this form, how much time it takes for a particle to coalesce completely and become a sphere, very important in controlling reactions in reactor engineering. And basically they formulated this an area reduction mechanism. They developed a rate equation. It looks simple, but the basic theory to arrive at that simple first order equation is quite complicated. But they developed the time for so-called model for what is called as the tau fusion. So that is an additional development which we are not going to deal with. So we are essentially going to go into the liquid drop equivalent model even for solid particles. Every time a particle is formed, we are going to spread the monomers around and make it look like a sphere. This is something we will adopt to begin with. Of course, when we speak of coagulation, there are two questions. So this kinetics is one. So since Marian von Smoluchowski, until about 1980s, most of the efforts was on kinetics, which is what we are going to again talk. However, since 80s, the question of structure became important. So if it is going to be formed irreversibly by sticking, is it going to be a random pattern? You know, like grains strewn around on the floor, or is there an order and structure in this? And very fascinatingly, that structure was found. It is called the long-term correlations by phenomena which are totally random. Apparently there is no correlation. Particle B comes randomly, nothing to do with the structure, but overall a pattern emerges, and that gave rise to the theory of fractals. Today, fractals are used very extensively to describe, in fact, any aggregated structure as a simple measure or a metric to quantify it. So the fractal theory is inherent in the so-called structure theories, and those theories are very complex. We are not going to deal again with the study of structure. Well, this is just to say that the origin of this, I always like to say that the whole of fractal theory is actually of aerosol origin. The very first evidence for the occurrence of structure in aggregates, that there is a pattern and there is a correlation, came by the work of Forrest and Witten in 1979, who used actually silver aerosols and then established by correlations the fractal dimension, established it. So yeah, that is what the importance is. Yeah, you have a question? Yeah.
In general, not just in this case, but whenever we have a network process, but in the large scale we see that there is an emission pattern, does that necessarily imply that like it is a fractal?
I didn't get the last part. Does it necessarily imply?
It is a fractal.
No, not necessarily. But it becomes useful to describe it as a fractal. So if it is not a fractal, you will get fractal dimension of 3. So be with it. It's a description. See, fractality is a model. In the entire aerosol physics in the 70s when I was just joined, everyone was calling it as an irregular aggregate with some porosity. That the fact that the porosity depends on the size was what fractality, only new thing that it brought in. Otherwise, porous structures were known. So it could be just a porous structure. Like I give the example, the cloth you buy is porous, but if it is a fractal, the shopkeeper would lose like anything, because he is giving you by meter, and if for 10 meters the material will be far less than the material if it is a compact object. So it is a porous object, very highly porous, but not a fractal. Aggregates, their density falls with their sizes, so they become fractal. So this is a test. If you have two different densities for two different sizes, it is likely to be fractal structure. So that is why you look for scaling and self-affinity and all this, the additional tests. Coming back, why do we study coagulation from aerosol perspective? One, of course, you have emissions, all starting from combustion level. So you want to describe finally how many particles it introduces to the atmosphere, what size particles actually come out. We don't get nano-sized particles, we don't get 1 nanometer, but we know they all started with 1 nanometer. So then you need to model. So coagulation becomes central to explain that evolution from sources. I come from nuclear originally, from Bhabha Atomic Research Center. So one reason why we were studying is basically to provide some pre-assessment of the impact if a nuclear aerosol, nuclear reactor suffers a very, very unlikely but high consequence accident. One example, it maybe happened in your lifetime, you would have seen, is the Fukushima, after all, 2011, right? It was a living example for us of a reactor accident. So why do we need aerosols? Because if a reactor, what's a reactor? It's in a simple picture, you have a containment like this, and there is a core, and in the core you have fuel rods, and then lot of cooling, and then lots of things happening. And in case there is a temperature surge, then core will melt down, and then steam will be generated. Along with this steam, then whole thing can rupture, the whole thing can break up and then give rise to particles, and still the outermost containment would contain these particles, and these particles are super radioactive. If for some reason, if the containment breaches at some level, because there is a lot of hydrogen produced, which happened in Fukushima. Fukushima, the lid itself blew off. So all aerosol modelers were very unhappy, because nothing to model, the whole thing came out. And if such a thing happens, breach occurs, then this plume of radioactivity will be released to the atmosphere, and the entire global long-term risk associated with the reactor for a far-field person is about this fear of aerosols, of inhaling radioactive aerosols. And then it becomes very important, before you build a reactor, to provide an estimate of the probability and the consequence of such an accident happening. You won't get a license otherwise. It is for that reason we had to study how these aerosols, if ever they get released, how long they will survive inside the chamber, because they will be removed by plate out, they will coagulate, become bigger and wash out. And if the breach occurs after that, then risk is less. So for that reason we were studying aerosols in a containment, and lots of studies were, of course, with metal oxide aerosols, and coagulation is a very central part of describing the behavior. This is just to show there are some very fascinating effects associated with coagulation. This is an experimentally observed thing. Still it is not modeled, but I know that is to be modeled by coagulation. See, if you have, this is a study in a chamber like this, you put lots of aerosols and just observe their decay. There is some pointer. Okay. So, you see the red line, it started with much less concentration, 0.3 gram per meter cube. Look at the black one, it went up to around 0.9 gram per meter cube. They were identical size wise, both of them. But you see after some time, after about 400 minutes or so, this is the log scale mind you. So, the one that had higher concentration originally came down, not just the number, the mass itself. So, this self-cleaning effect I call it, it's typically non-linear, is singularly because of coagulation. So, that is where one has to, some fascinating interpretations can be made. One has to study coagulation to explain this kind of crossover behaviors, call it crossover behaviors. Yeah.
So, suppose you have two populations of aerosol, one radioactive, which is fairly low number concentration as compared to the not aerosol, which may be much higher. Then is there a worry about coagulation of one radioactive with a non-radioactive aerosol?
Yeah.
Which that chemical might be in fact more.
That is what happens in the atmosphere. The cesium-137 released is actually very sparse, very dilute, but it attaches to the existing nuclei and then it acts like it is vectored by the background particles and it precipitates and all that. So, atmosphere cross attachment occurs. Very rarely the cesium to cesium collisions take place and grow. Yeah, but collision is concerned, it does not matter whether it is radioactive or non-radioactive, more or less the physics size only governs it. Yeah, this is a very interesting another maybe something we observe routinely. Why plumes change color, right? So, when it is just emitted, they look black because carbonaceous, very small particles, most absorption. Very soon, within seconds, they appear brown, gray, because they grow into about 0.2, 0.3 microns. Then they become so dilute, they appear white. So, this is more or less, not entirely, but predominantly again an effect of coagulation. So, this is just to highlight. And I have been dealing with this related question of how do you account for, Professor Chandra and me, we are working on this together, how do you account for, and of course my BRC colleagues with them. So, how do we account for transformation that takes place from combustion sources as the particles ultimately become a part of a atmosphere environment and eventually participates in other global processes. So, this is where the concept of near source modeling becomes. If a code has to handle source by source, it is an enormous task. So, if you can therefore generate some kind of a semi-analytical model for the near source transformations to be able to predict the sizes which become a form of the background system, then that is very advantageous. So, that is where coagulation, understanding coagulation mechanics, how to handle and obtain certain levels of analytical solutions, that becomes very useful. The complexity with this problem of emission sources becoming a part of the background is, it is not just coagulation, it is dispersion and coagulation together. So, one should know how to handle the processes of transport and coagulation together. It's a very important application that one is able to come up with to explain ultimately the kind of sizes to which the particles grow.
In the atmospheric context, for example, an outsider might feel like it, suppose everything is, because the atmosphere is infinite in dimension, in terms of scale. It's not like the homeopathic kind of dilution that happens. Very small kind of diluting so much that all the effects become negligible. They're all always localized spatially with that's all. It doesn't like dilute in the infinite space so much that it becomes inconsequential.
Yeah, it doesn't become inconsequential because it adds to the background. The existing, it becomes a part of the background system and many of them being anthropogenic have their own properties, like if it is carbonaceous, its light scattering properties are very important, things of that type. So, it adds to the overall loading of the atmosphere. So, in that sense. So, each source has to be modified slightly to account for that overall loading. That is what I am talking about. Yeah, they are consequential, they do not become zero effect. That is not the aim. You can use GCM and other circulation models with this corrected source term and then propagate them around the globe. I mean, that is the idea.
Also that, what as we pointed out, that near source changes that also affect the overall optical
properties. Yes, in fact, that is right. So, guided by her,
and then that will propagate into the radiation transfer at the end.
Yeah, this paper by Tanmay in fact showed significant changes in the light scattering properties. I have not shown it here, but yes, that was a recent publication we had. Yeah, so in aerosol engineering, as I mentioned, the work of Friedlander dealt with self-preserving distribution as primarily to be applied to aerosol engineering in addition to application to atmospheric science. And there the key question would be in most aerosol reactors, if one has to just sort of sketch it, it would be like I have a tube and then I have some introduction of some precursor molecules, say TiO2 molecules are formed through some reaction. So, I introduce titanium oxide molecules, then I maintain a certain level of temperature gradient, say very high and let us say T very low, and in this process I control the rate of growth, because I do not want agglomerates many a time. There could be applications where we may like to have agglomerates, but everybody wants, or most industries want, a spherical TiO2 particle, and in which case how to avoid coagulation requires you to know about coagulation. That is where the major modeling comes, and here you maintain the temperature gradient in such a way that the TiO2 particles does form sticking, but undergoes surface rearrangement, coalescence. So, up to certain distance, up to the growth of about 50 to 100 nanometers, they remain spherical, but you cannot control beyond that. These are solid material. So, very quickly they start forming aggregates. So, to control reaction engineering, one has to again understand you have to model the whole system via general dynamics equation, including coagulation. So, just to, now that we mentioned sticking, we have to know a little. Sticking is a very complex mechanism. Addition to surfaces is separately modeled, but in aerosol coagulation theory, we do not model sticking. This is something, but we must know how sticking occurs. So, when particles come together, any surface, aerosols, the ubiquitous behavior is they stick to surfaces. So, there is a ubiquitous van der Waal attraction, that is the fundamental thing. But van der Waal attraction is molecule. So, for a particle there is a modified van der Waal because it consists of many molecules, and those near the surface and the molecules here, they will form a lot of cross attraction, and this collective thing is called the Hamaker force, or Hamaker potential, or Hamaker force. Okay. So, Hamaker force is basically pairwise summed van der Waal attraction in a simple explanation. So, whatever that force is not 1 by r to the power 6, it is 1 by maybe d 1 by r or something, I fully do not remember, but it is much power law is very different. In any case, the last leg, as the particle approaches a surface, there is an attractive potential. So, it is attracted to the surface, and somewhere there is of course this, the particle sits in this and it equilibrates with the surface. If it does not equilibrate, it will bounce back. So, they become partially sticking problems. In many aerosol contexts, especially nanoparticles, this partial sticking is also important. You cannot assume them to stick all the time. It's possible that they bounce back. In impactors, again, non-sticking properties are very important. High speed impaction, particles bounce back. So, here somehow we assume that the depth is, the potential depth W is much more than kT. So, W by kT should be much greater than 1, and then there is irreversibly they get bound to the surface. So, sticking is basically therefore a nano layer process. This whole range could be of the order of a nanometer. Typically in aerosols, if two aerosol particles, when we say they have stuck, the modelers assume this gap distance to be about 4 angstroms. Typically, there is equilibrium distance assumed. Typically, there is no hard and fast proof of it, but Friedlander and others have generally used this 4 nanometers as the interparticle distance even after they have stuck. So, sticking is a very important concept. Yeah. So, I mean the second part simply says the path that it traverses to come down to here is much larger than the range or of these dispersion forces. Van der Waals and others are called dispersion forces. So, it is much larger than that. So, most of our efforts is in this part of the aerosol system. This is of course bit more detailed way of classifying the aerosol mechanics of growth and attachment into various regimes. As we know, aerosols have that uniqueness of being in a transition regime, where the particle sizes of the same order as the mean free path. In liquids, there is nothing called transition regime. There is a mean free path is much smaller than particle diameters typically. They are all in angstroms, and here we have microns. So, when the particle is transported from the far off point like the blue line is for example a trajectory of a particle going to get bound onto a sphere at the center. So, the region 1 is where it collides with the air molecules in such a dense fashion that you can describe it more or less by diffusion and Brownian motion. So, it is in fact sometimes called as the diffusion mobility regime. Classical Brownian diffusion suffices. Then it comes to region 2, where the collisions are now rare. It is not because the gas density has changed, but now it is closer to the surface of the particle. So, from flight from region 1 to region 2 is of the order of let us say 30-40 nanometers. So, mean free path is of the order of 65 nanometers. So, very likely that it does not collide with any particle, or it collides with only a few particles. So, that is where you have a mixed kind of gas dynamics, or you use basically rarefied gas dynamics. Sometimes you consider it as a free flight. Starting from the outer regime, you throw them like ballistically, like bullets. Occasionally, you allow for single body, one body interactions. It is called one collision model. So, these are all used in many theories. Now, region 3 and 4 are the ones where you have collisionless Hamiltonian, completely collisionless motion, where conserved energy transport takes place. All the energy it has gained because of attraction and all that is conserved. You treat it, when I say Hamiltonian, I mean energy conserving motion, until it falls to region 4, where you have the dispersion forces and then surface forces, they act together to completely bind it out. So, this is by, I think by Ruckenstein, Narasimhan and Ruckenstein gave this classification for understanding the various stages involved in coagulation. Yeah, this we had already learnt, but now as we enter Brownian coagulation, that concept becomes very important, the concept of the so called particle Knudsen number, which we mentioned, correct. So, it came from the concept of a Brownian path length. As Professor Chandra mentioned, it's actually has to be defined not like gas molecules, but if there is a Brownian particle which is projected, let us say at any instant of time, the particle is found to have, let us say, x component of velocity. Now, you just wait how long it takes on an average for this velocity to be completely perpendicular to it, that is this component to decay, right. So, that distance is called the sort of equivalent of a stopping distance in that, but here we call it as the particle Brownian relaxation length. What is the notation we use? Maybe lambda p, yes. Simple models you can build, because my particle is being thrown also by a thermal system, it is not external. So, you can consider it as the velocity of thermal velocity c bar with which the particle is thrown on an average, and the particle relaxation time. So, this is the stopping distance, and this is when the particle on an average would come to 0. So, this actually will be a simple model of Brownian relaxation length. So, you can say tau is what? Right? Tau is mass by friction coefficient. So, this now you express in terms of c bar is root of 8 kT by pi m, and mass you can keep it or you can express it in terms of diameter and all that, and Fp as usual we have 3 pi dP into mu, and I think Cc will go up, right, and Cc. So, we come back to our old expression by an explanation starting with its thermal velocity. So, why it is important in coagulation is, somewhere during the development of the theory of coagulation, and in the early years of coagulation, people were actually dealing with mean free path as we spoke about in the context of single particles, which is mean free path of gas molecules. But however, when the particles and particles are going to collide, do we consider that as the metric? Is that the length scale to worry, or is this the length scale to worry? And we know that this is about 20 nanometers somewhere, typically, not 66. So, it is a huge difference, significant difference. So, then I think again folks who formalized it by saying that when we talk of coagulation, the metric, the primary length scale should be corresponding to lambda p and not lambda g, if we call the other one as the gas related mean free path. So, essentially therefore, you will see in literature talking of Knudsen number, classical Knudsen number may be without a subscript, but particle Knudsen number as defined by 2 lambda p by taken analogously with gas molecules. So, this becomes a very important concept.
Well, would you want to reflect on this, that for gases, roughly the mean free path will correspond to its density and to the pressure?
Yes, yes.
But in the particle case, which is much rarer, the lambda p is actually the diffusive time.
That is why this definition.
And so it's much shorter actually, because if you go by density, it's much rarer, and so the distance, actual physical distance between two particles is way higher than
much higher. Yeah, I forgot to mention that. Now that you mention, we also have another length scale. So, if I have particles in an air with their concentration n, then if I take a photograph instantaneous, then I can actually calculate the interparticle distance. That is another measure. What is the interparticle distance for an aerosol? Do we have an idea? Supposing I have a dense smoke, 10 to the power 12 number per meter cube. The smoke looks so full cloud because of the light scattering, but interparticle distances are quite large. For example, the formula for interparticle distance is calculated very simply like this. It is just one particle. If the interparticle distance, let us say, is dc, then in a volume dc cube or volume of a sphere dc, concentration is n. So, there will be these many particles and that should be 1, because it is interparticle distance, one particle located at the center of a sphere. So, you break the entire volume like this. So, you have a simple law that the interparticle distance will come as a pi n, 6 by pi n to the power 1/3. So, roughly it is n to the power minus 1/3 law, right. So, if you have 10 to the power 12 particles per cc, which is a dense aerosol, not very light, you will have 100 micrometers or so, 10 to the power minus 12 by 3. So, which is 10 to the power minus 4 meters, right. So, it is about 100 micrometers. So, typically this will correspond to 100 micrometers, which is much larger than aerosols of our interest. So, that is why this cannot be used as a length scale, as such is of no consequence in aerosols, whereas this is much more relevant that way.
And what is the order of this lambda p?
20 nanometers. So, I mean, you can see that it varies 20 to 12 and goes up, but I think it was generally taken as 20, right, of that order.
10 is 20.
Yeah, it comes down to 10. You can see the minimum is at 10.
It's the same as the path length.
It's the same. Mean free path is the same as the path. It is in fact path length only.
Yeah.
Called as the Knudsen number. I don't think people don't call it as a mean free path. If I have used that jargon, I am not correct. It is called as the Brownian relaxation length, in terms of which we define a Knudsen number in analogy with the mean free path for the gas. That's it. So, it is a Brownian relaxation length 2 lambda by dp, where lambda p is the Brownian relaxation length. That is the more correct way of putting it. Now, there are many mechanisms which cause coagulation. We will deal with some of them. The fascinating subject. Brownian motion is the most ubiquitous, and most aerosol physics, when we deal of either in smoke or in describing small particles in the atmosphere, other than cloud physics or something, we will be dealing with the Brownian coagulation. So, we will discuss it extensively. However, fluid shear causes also coagulation. In fact, you know, the coagulation theory got transferred to the subject of gel formation in 1980s via the shear coagulation type models, where even the formation of sol gel transitions were essentially a coagulation phenomena, where the coagulation rates were controlled by something like a shear equivalent rates, very high rates. So, as they say that when your pipe, let us say, carrying water and water is dirty, and slowly the pipe starts clogging. Initially, you do not notice the flow rate change that is happening, still water is flowing, but if suddenly it can so happen that the structure struck on the surface of the pipe can grow into a multiplying structure very rapidly and block your channel. So, this kind of rapid growth or formation of megastructures, it is called spanning structures. In coagulation theorists call it as formation of spanning structures, that is end-to-end spanning. It happens in aerosols also, but rarely. This is by coagulation you can get a structure which ends from one end to another end. For example, the formation of a web-like structure in kitchen smoke is example of a spanning structure. You got a large structure occurring normally in the corners of your house, where there is a air shear takes place, and the particles tend to get accumulated there, and you have a coagulation, and that is why you will see all kinds of things hanging. Not all of them are cobwebs, many of them are your kitchen smoke aerosols eventually forming a mega structure like this. So, these are very advanced kind of phenomena, governed again within the framework of coagulation theory. And of course, fluid shear is one. Yeah, differential sedimentation is what causes predominantly the growth of raindrops. So, this is some of them. Then there are other intermolecular forces, then electrical forces of course are very important for charged particle coagulations, all that is a special part of it. So, this is basically to cover up the introductory part of this lecture. So, I have a few points just brought in here. So, if somebody asks you what is the most distinguishing property of coagulation, what would you say? It's a qualitative question, so any answer is as good. Let's see. Anyone? From whatever you heard from me, what is the most distinguishing part of coagulation? Huh? Yeah, that's a good one. Yes, one could say that. Without conservation of the number, yes. Changing number, yeah, that corrects it more precisely, yes. That's one, could be the one. Or growth by sticking, you can have another way of saying. So, second one I mentioned about there are far more CO2 molecules than say carbon atoms. But why do we not talk of coagulation of CO2 but of carbon particles growing, right? Anyone? Why don't we talk of coagulation of so it's just that there is van der Waals force. Every molecule has a van der Waals force, including argon. Argon is the weakest, though everybody studies argon for van der Waals force. But at low temperatures, CO2 will form a solid, so it does coagulate. So it is just that the thermal energy is larger than the Hamaker energy at those kind of distances, that CO2 is not going to stick. So you don't get it. So that is what entirely, that's what distinguishes the aerosols entirely from gases. So why carbon aggregates do not coalesce but water drops do? You get soot, right? Very ramified structure. Yeah, so that's right. It's a capillary force which introduces tangential components and then makes them spread around, not allowing them to get out though, doesn't allow them to get out. So that is why that internal rearrangement doesn't exist in carbon, or maybe very weak, maybe takes years, maybe months, like that. Yeah. Relative significance of van der Waals force and Coulomb force as a function of interparticles. Yeah, this just give you a feeling. So everything is attracting, charged particles of opposite charges also attract, Coulomb also is attract. So do we introduce all of them and then start solving a problem, or use our judgment to use one against or one as opposed to the other? So why would you select Coulomb and not do van der Waals? What is the reason? So one should have an idea. So here of course I mentioned, probably I didn't mention, but van der Waals goes as 1 by, potential goes as 1 by r to the power 6. Potential. Force goes as 1 by r to the power 7. So whereas the Coulomb, the potential goes as 1 by r. Right. So there will be distances at which Coulomb will act, even at micrometer distances from each other, whereas van der Waals will act only, it's a very short range force of the order of a few angstroms. Then it falls rapidly as r to the power 6. So we don't include them in transport much. Maybe in colloids they may be important. In fact, the entire DLVO theory is based on van der Waals and double layer repulsion and van der Waals. So because there the path distances are of the order of these forces only, that is why. So particle Knudsen number we just saw, you know what it is. Yeah, so I explained to you why a particle Knudsen number is going to be important. Difference between aggregate, agglomerate, cluster and a droplet. It's a kind of qualitative, but there is some people do use in some contexts like agglomerates and aggregates, as opposed to of course droplet. See, all the first three are those which probably do not coalesce at least, and droplet is the one which coalesces. Yeah. And aggregate normally is just a collection of particles. They just aggregate, like rice aggregates when hardened. Not much transport is involved. Maybe that could be a way of separating. Well, the last one maybe we can defer it when we go to hygroscopic particles and all that. We will revisit these growth mechanisms. Yeah, so in the next few minutes, we now start quantifying what we are saying. So, how do we describe this fundamentally nonlinear mechanism? So, you have to subdivide your concepts to be able to handle within some algebraic framework. We have various levels of understanding. So, we understand this first with the simple so-called bimolecular equivalent concept, then slowly expand it over to the many species or many size systems, equivalent systems. We can look at the magnitude of the problem that I will have, that I have particles of all possible sizes mixed randomly in space. So, when I say randomly, every size has equal probability of occurring everywhere in space. So, they are mixed properly size wise, no preferential size effects, and I have to consider collisions between every conceivable network of collision. So, here we borrow the concept from simple chemical kinetics. So, first thing I do is I focus on one particle and call it as, let us say, type 1 particle, and let us say I have group of type 1s and I have type 2 particles. We only look at only two sizes, let us say two sizes equivalent, and let us say this concentration of this is N1 and this is a concentration N2. Then I can say, if I sit on one and assume that two particles are essentially around it, ignore the other ones, then I can assume that there is a steady flux of two particles on one. So, that flux, if I know from some theory, I have the one rate expression of rate of two type particles arriving on one particles per unit time. If I linearly now add that rate to all one, then I will get the total number of such encounters which take place, say, in the given volume. So, this is the elementary concept of chemical kinetics. Yeah, yeah, we will take care of double counting. I am going to do that. So, in the first picture, you are right, of course, it is very important, but we will take care of that. So, you define therefore the total encounters as some K12 N1 N2. This is total number of encounters that will take place is proportional to the concentration, the linear model of each of them if there are two species. 1-1 interaction is sort of ignored, let us say. In fact, anything that interacts we can call it 2. So, this is the elementary beginning of an understanding of how we are going to model it. So, this K is a second order rate constant. Second order, it is a dimension of meter cube per second. So, from a practical perspective, one would always extract this K12 by making measurements of such encounters and dividing by individual concentrations. That is how we practically do it, and hope that when you do that you get a constant. It does not depend on N1 and N2. That guarantees that our assumptions are correct. So, that is the way we always work. We first make an assumption, then experimentalists will have to verify that that is correct. Then that model is okay. So, that is what the initiating concept is. I think the other part is already I mentioned. And most I would say an abstraction is the idea of probability currents. Actually, this concept of probability current is necessary. If you actually see in a gas molecules, in any small window of time of, let us say, a microsecond also, 1 microsecond, there will be, every molecule will be facing so many such collisions, maybe hundreds or thousands of collisions even in a narrow window of time. On the other hand, when we are talking of aerosols like this, very dilute, 10 to the power 12 per meter cube is what the aerosol is. Do you know how many gas molecules are there in meter cube? Anyone? Vidya, Azam, any of you? Just to give an idea of the numbers we are talking about.
You can just use
Yeah. Avogadro 10 to the power 23, but it is 10 to the power 25 molecules are typically there in air at STP of that order. So, imagine, and the aerosols never reach that level. Then 10 to the power 13 is probably the highest aerosol. Any more than that, the coagulation is so rapid, they are brought down to 10 to the power 12, 13's level. So, when you have such small numbers in a short window of time, number of collisions are 0. If you see a particle, you have to wait for long length of time. So, but then we continue to use diffusion model in aerosols. So, what justifies there is not the real current. So, if I have a particle, even though I postulate the current of other particles on it, these are probability currents. That is, if I wait long enough under identical system, I may have a couple of particles come, and on average, if I divide by the time, I will find this current. That is the way. So, although we are talking exactly as if chemical processes are taking place by diffusion, what we have are in the back of the mind that these are all probability currents. When we are discussing again aerosol systems, we are going to talk of binary encounters, as I mentioned. At any given point in time, in an aerosol like this, if I have one particle, at the most one particle collides with it at a given short interval of time. Not very unlikely that two simultaneous collisions take place. So, the encounter is more of binary, which is quite valid, because as I mentioned, most of the times it is probability currents only that are happening. So, this assumption is made. Let us now think of how do we start modeling this growth. So, if I have aerosol particles of two different sizes, say this is 1 and this is 2, or size could be dp1 and dp2, first thing I will sort of make an assumption that there is no other external force, no field. Most likely cause of them coming together is some Brownian motion. It's also going randomly here, no forces. This is also going randomly like this, and sometime in the course of their random motion, they may be at the same collocated within their d1 plus d2 distances, and they stick. Then the van der Waals force takes over and sticks them. That means, if I see from my laboratory framework of space, I will see Brownian motion of both of them. They are of comparable sizes. So, how do I model diffusion when you have the encounter of two different Brownian particles has to be done? This simple Einstein law of diffusion becomes very handy to describe the joint Brownian motion of two particles. So, what I do is, let us now ask the question, supposing I sit on these particles, I shift my frame here and observe the motion of the other particle, would it be different? Will its diffusion coefficient look different? Let us see how that happens. So, I take the laboratory framework, I have particle 1 and let us say particle 2, this is R1, this is R2, this is R12, right. So, if I sit on one and see, it would look like a diffusion in the R12 space, whereas in the real laboratory we are used to describing the diffusion of R2 vector and the diffusion of R1 vector. So, we basically have to express R12 in terms of R1 and R2, and then my job is done to explain how the diffusion would look if I sit on one particle. So, you know that you write R12, I sort of at the moment ignore putting a vector sign, you understand it, we are talking of actually vectors, okay. So, it is, let us say it is R2 minus R1 or R1 minus R2, maybe we will take it as R1 minus R2, right. So, any small change that has taken place at a short time delta t. Now, you wait for at a t, let us say this is what it is, and wait for a little more time delta. Each of them has suffered a delta R1. Right. Now, I know that this is random fluctuation. I can't assign much meaning or make measurements of individual motions. So, I do an ensemble average or a time average, and generally they are equal. So, if I do an ensemble average, I will take, it is wiser for Brownian motion, we learnt it, that you square and take the ensemble average, because sometimes the mean displacements are always 0, they do not lead to any original result, whereas the measure of displacement is a square and average. So, I square it, you are going to have delta R1 square plus delta R2 square minus 2 delta R1 dot delta R. Vectors, but remember that. So, now if I take expectation of that ensemble average, correct. Ensemble average means what? You must have that picture in mind. Similar replicas of systems. Two particles, imagine there are thousands of such two particle systems. Each of them will behave differently, but when you square and average, a pattern will emerge. Now, we know most importantly that since particle A and particle B are independent of each other, no correlation, their vectorial correlations will be 0. Actually, it will be R1 R2 cos theta, and cos theta average is going to be 0 when you do that angular this thing. So, this we take as 0, it is independently distributed in a system. So, moment you do that, we have this relationship. Now, we invoke the Einstein result for each of them, and Einstein result says, anyone remembers how do I relate it to time? How do I relate the mean square displacement to time? Louder. 2 dt, right. So, that is the key thing. So, we have delta R1 square average is twice of d1 into delta t. So, is it for delta R2 square expectation to d2 into delta t. So, my delta R12 square should be equal to 2 of d1 plus d2 into delta t. So, my effective diffusion coefficient d12 as seen by sitting on particle 1 would be d12. So, d12 is d1 plus d2. It looks, it's very simple, but makes it so big help in going further in modeling, because I can now sit on one particle and observe the neighborhood and see what is happening onto that particle. So, armed with this very important knowledge, we now start modeling the first model for coagulation. This is called the Smoleshevsky, is a stationary sink model. It is used so often in theory that it is forgotten that it's Smoleshevsky's first model he built, although he is remembered more for, I mean equally, not more, for the sticking condition. That is the key issue. So, Smoleshevsky's stationary sink model. So, all these words are loaded. Stationary because there is no relative convective motion. They are not having either gravitational sedimentation, or they are not moving in electric fields, or they are not moving in shear flows. They are in a stationary fluid. Now, sink is the key word. So, as I mentioned, how do I describe the sticking? I do not want to use van der Waals forces and start struggling with lots of complications in the neighborhood of particles which are just going to, which have just encountered and have reached within that angstroms. How do I handle? I can handle transport. We know that we are going to use Brownian motion equation. We know it. But how do I handle sticking? Smoleshevsky is the one who made the key assumption. It is called the Smoleshevsky boundary condition, that we can forget all the intermolecular forces and solve the equations with just the boundary condition that the density n at the surface of contact, say in this case d1 plus d2, let us say, at all times is 0. It is not d1 plus d2, I must say r1 plus r. If the radius is r1, held at some point. Basically, at the point of contact, we hold the concentration is 0. I can say C or N, okay. You meant this, right? Yeah. Yeah, C, let us say C, concentration as 0. Very innocuous, and it also jibes well with the concept of a diffusion equation, because it needs a boundary condition. So, we are providing one of the boundary conditions. It needs two such conditions for solubility. So, one of them is provided. But this became very controversial, although there has been 100 years development on this sticking condition itself, because it violates simple, maybe I will just mention it. It actually violates the gas kinetic structure of matter in some ways. So, people had to abandon it partly, but results do not change much. Much of the practical results that we work with, more or less we get by the sticking conditions, unless there is a significant bounce off or something, in which case you can modify. There are more generalized conditions possible. So, we use for the present this condition. So, armed with this condition, we now set up the equation of Brownian motion. So, what is my equation and what is my model? So, as I mentioned, I just consider two species. It is a two species problem. I am still not gone to polydispersity. I am considering, let us say my one type particle, I am sitting on it. Let us say it has a radius, notation I use R1, yes. And I distribute all the two types particles around it, although I am treating it is a probability distribution. It is actually probability density distribution ideally, because you do not have so many particles around it. At any point in time, their interparticle distance is 100 microns, I already saw. So, within the range of 1 micron, where the diffusion acts, hardly there will be any particle at any instant of time, but there is a probability density, that is why. So, we distribute all the two particles around and call the two particle concentration as at the moment C, as measured from 1. So, I call it this, I call it as R at a distance C. And all that I have now So, at t equal to 0, I have taken a photograph, they are all uniformly distributed, C is around 1. Now, I switch on my diffusion process, which is Brownian motion, and describe it via diffusion equation, because Brownian motion is for all practical purposes described by the diffusion equation. So, that diffusion equation for C, taking into account the fact of the joint diffusion that we just now derived, is going to be this. Well, it should be in spherical, yeah, okay. I am going to use in spherical system. Again, isotropy is assumed. Again, my distribution is isotropic, so I do not need angular dependencies. So, theta and phi terms are dropped. So, in the spherical coordinates, my diffusion equation is going to have this, and I need 2 boundary conditions to solve them. Yeah, we stop it here. So, I have one of them is going to be concept of reaction radius comes here, C R1 plus, sorry, C0, let us say, C0 at all times is 0, not what am I doing, R1 plus R1. There is no concentration of the 2 species here around it, that is the idea. It cannot exist. If it is there, it should have formed an aggregate. It is actually Fuchs made a very nice statement, which in a way obviates this conflict of sticking condition with kinetic theory. Conceptually, he said, I define my C as the concentration of airborne particles. So, obviously, when R1 plus R2 at that point, airborne particles are going to be 0, because it is form an aggregate. So, then C equal to 0 looks quite naturally consequence of this statement. So, we do that. So, C of R1 plus R2 at t equal to 0 and C at infinity far away at all times will be some maintained concentration, but let us say C infinity, the original concentration. So, these are the 2 particles, and C of course at t equal to 0 at all points of R is uniform, again C infinity for all R greater than R1 plus R. This is my domain. The second assumption is a nice one, in the sense, how do I know it is going to remain? My coagulation is going on, would it not deplete all the particles? And that is the beauty of 3-dimensional diffusion, that it allows for the survival of particles at large distances. A steady state solution exists, but in any case mathematics is the guide. So, if it allows for it, well and good. In fact, in 2 dimensions it does not allow. If you have to consider aggregates of on a surface of a liquid, for example, 2D diffusion on a planar surface, you cannot have a second condition, because eventually there is no solution for diffusion equation in 2 dimensions, steady state diffusion equation. So, but people handle it differently, I think, but for us we hope a solution exists. So, in the next lecture we continue with solving this equation and further. Thank you.